Hi everybody. In this section we're going to talk about something called improper integrals. Let me give you a scenario that will kind of lead into what we're doing here. Suppose the function s of t gives the rate of change of sales of a product in units per year, where t is the number of years since the product was introduced for sale. Let's recall how to interpret some definite integrals of this function. The definite integral from 0 to 5 of s of t dt would be, one way to interpret what that means is to think of areas. So if I take the definite integral of s of t from 0 to 5, that's going to give me the area under the curve s of t going from year 0 to year 5. In terms of the actual number of sales here, we can interpret this as the total number of units sold from year 0 through year 5. What about the definite integral from 5 to 10? Again, we can interpret this as an area. It's the total area under the curve between 5 and 10. But in terms of sales, it would be the total number of units sold from year 5 through year 10. Keep in mind that s of t is the rate of change of sales. When we integrate it, we get accumulated sales. The definite integral from 0 to b would be the total number of units sold from year 0 through whatever year b is, which can also be interpreted as the area under the s of t curve. Again, s of t is not the amount of sales, it's the rate of change of sales. Now, suppose we want to know total sales for all eternity. We could write something like definite integral from 0 to what of s of t dt? Well, we could put something like infinity. We don't want to put an upper limit on the year. We want to say through all years for all of eternity. But what would we mean by that mathematically? What we're really saying is, at least in terms of area, we're saying what would the total area be if I take this right-hand edge, this upper limit of time, and let it go to the right forever and ever. In other words, let that go to infinity. That's how we're going to define this definite integral. We're going to say what this means is the limit as b goes to infinity of the definite integral from 0 to b of s of t dt. So we're thinking of extending this to the right with no end in sight. More generally, we'll define the definite integral from a to infinity of f of x dx as the limit as b goes to infinity of the definite integral from a to b of f of x dx. So I've given the name b to the upper limit of integration here, and then said I'm going to be taking the limit as that upper limit goes to infinity. When you have an infinity in an integral, it's called an improper integral. So that's what's meant by the title of this section. It means we're talking about integrals that have an infinity as a limit of integration. Now this formula that I've just written here is number 1 in the box at the top of page 438 in the textbook. We're not going to be covering formulas 2 and 3 in that box. What's different about them is they have an infinity as a lower limit, and we're just not going to go there. I don't think we need to for this class. Next, we'll see some examples of evaluating these.